Hello, my name is Sara Todorovic from the University of Technology in Chemnitz, and I will present our work on preferred mental models and syllogistic reasoning. This is a pre-recorded presentation for the 21st International Conference on Cognitive Modeling. All red shapes are circles. Some red shapes are marked with a star. What, if anything, follows? This is an example of syllogism, one of the core domains of examining human reasoning abilities. It consists of two quantified premises describing the relationship between three terms. Here, specifically, the premises have the quantifiers all and some, and the terms are red, circles, and star. The task is to conclude what kind of relation, if any, exists between the two end terms. There exist at least 12 theories that aim to explain and model processes behind human syllogistic reasoning. In this talk, we focus on the mental model theory, or MMT for short. MMT postulates that given some observations, individuals create iconic representations, so-called mental models of possibilities. Basically, they create a subjective mental representation of the information presented in a reasoning task. For example, let's look at two possible representations for the given syllogism. On the left, we see a mental model with two instances. The first one describes shapes that are circles, red, and marked with a star. And the second one describes only circles that can be any color and marked anyhow. These square brackets denote that the set of entities described by the instance is exhaustively represented. On the right, we have a mental model with three instances. We are already familiar with the first two, and the last one describes entities that are not circles and are not red, as denoted by the negation sign. Both support the logically valid conclusions. Some circles are marked with a star. However, to confirm this validity, one should think of all possible interpretations and check if they hold. Increasing the amount of possible representations can make solving such problems quite difficult for humans. In the spatial relational reasoning domain, it has been repeatedly shown that individuals have preferred mental models. They prefer creating some models while struggling with others. However, the model building process in general is typically not addressed in the syllogistic domain. Namely, experimental setups do not examine which models do individuals create, if they're correct, or if they even have preferred models at all. We've conducted an experiment where participants had to provide visual responses that show the representation of given syllogistic premises. With that, we tackle our first research question. Can we examine what kind of models do individuals create from the premises of syllogistic tasks, and do they have preferred mental models? In mathematical and computer sciences, the minimal simplest representation of an expression is referred to as its canonical form. In the context of mental models in the syllogistic reasoning domain, this concept denotes which entities form a canonical set for a given syllogism and which non-canonical instances do not have to be present in a model but are still consistent with the premises. For example, for the syllogistic premise, all red shapes are circle, we have circle and red, which is a canonical instance, whereas not circle, not red is not. With canonicality, we can assess the incompleteness of the model in terms of covering all possible interpretations. By analyzing our participants' built models, we tackle the first part of our second research question. How influential is the canonicality of mental models that individuals build for syllogistic premises on the correctness of derived conclusions? The most prominent implementation of MMT for syllogistic reasoning is the Lisp-based model MReasoner. Distinguishing between three systems, MReasoner creates intentional representations of premises in System 0, builds and interprets an initial model in System 1, and performs a search for counterexamples in System 2. For our work, we are interested in System 1, which parameterizes the number of entities in a model and their canonicality, specifically the likelihood whether they are drawn from a canonical set of typical entities or the full set of entities consistent with the premises. By comparing our participants' built models to the output of MReasoner's model building stage, we address the second part of our second research question. Is the model building behavior observed in humans in line with the model building processes of MReasoner? Before I present our experiment and analysis, I will give a short theoretical background overview. First, syllogisms. The two syllogistic premises and conclusion are characterized by their quantifiers or mood and the term order or figure. We take into consideration the four first-order logic quantifiers, all, some, no, and some not, abbreviated by A, I, E, and O, as shown here. The order of the subject A, predicate C, and middle terms B in the premises determine the figure of the syllogism, as shown here. Using the abbreviations and figures, the syllogism, all red shapes are circles, some red shapes are marked with a star, can be denoted using AI4, where B, the middle term, is red shapes, A, the subject, is circles, and C, the predicate, is star or marked with a star. Similarly, the conclusions are denoted by using the quantifiers abbreviation, and they take into consideration the direction of the end terms, AC or CA. So, for example, some shapes marked with a star are not circles is denoted with OCA. And finally, no valid conclusion is abbreviated by NVC. According to MMT, when given syllogistic premises, individuals represent the entities described by the quantifiers using mental models and aim to derive a conclusion based on that. Before accepting the conclusion, they engage in a search for counterexamples. If the search is successful, they will reject the original conclusion and will either correct it or conclude NVC. M. Risner implements these processes using four parameters. Lambda determines the size, the number of entities in the model as drawn from a Poisson distribution. Epsilon determines the canonicality, so how complete is the set of represented possibilities. Sigma describes the likelihood to engage in a search for counterexamples, and omega decides what happens when a counterexample is found, whether the conclusion is weakened or NVC is returned. Now that we know all we need from a theoretical perspective, I will present the experiment we conducted. The main objective of the experiment was to obtain a visual representation of the participants' preferred mental representation of a given syllogism. The presented syllogisms described objects in terms of their shape, so they can be a square, a hexagon, triangle, or circle, their color, red, yellow, green, or blue, and their mark, a star, cross, plus, or diamond. So, for example, the syllogism EA2, with hexagon as a subject, yellow as a middle term, and star as a predicate, reads, no yellow shapes are hexagons, all shapes that are marked with a star are yellow. Then they can use the selection box over here to pick their desired attributes and assign them to a placeholder object. Ultimately, they end up with a representation like this. And after sharing the representations visually, participants also had to select which of the 9 responses follows for each syllogism they were presented with before. We now move on to our analysis. First, the experimental data. We analyzed the correctness of the provided representations and found that circa 82% of them were correct, and the mean correctness of models by syllogism is visually represented here. We compared the best and worst 32 tasks and found that correctness does not seem to be affected by negativity of quantifiers, particularity, or validity. We only found that figure 2 leads to more incorrect models, and figure 4 seems to be a little bit easier. Regarding the selected responses, in the second part, only 31% were logically correct, and in only 25% both the representation and response were correct. However, we found no significant correlation there. Here, we illustrate the response distribution among all participants and contrast it to a neutral control dataset. We can observe a tendency for participants not to choose NVC answers as often as in the control data and to avoid the CA direction in the responses. This implies that there was a belief bias effect among participants, so some sort of superficial beliefs and background knowledge were induced by introducing a world with a discrete amount of possible object attributes. Here, we can see that participants preferred mental models only for the syllogisms that have a unique preferred model. The shading indicates the proportion of participants creating a model with those instances. So, for example, for AA2, there is a strong tendency to build a model that contains instances with the terms presented in the syllogisms and instances with any other term. On the other side, for 001, For example, there is a much weaker tendency to create a model that only contains instances that are the subject of the syllogism and not anything else. We can note a tendency for syllogisms with an A premise that they contain non-canonical instances a lot more often. That is likely because they're easy and do not introduce errors when added. Additionally, we can see that the syllogisms with particular quantifiers, so namely some or some not, tend to be given by a smaller proportion of participants, which can be associated with the quantifier's low informativeness, therefore allowing for a bigger variety of interpretations. For AA1 and EA4, they're not visualized here, we found that there were two models that were the most preferred by an equal proportion of participants. And the rest of the models, we did not find any patterns that suggested existing preferred mental models. Finally, I will present our analysis regarding mReasoner, specifically comparing mReasoner's created models to our participants' answers. The two parameters relevant for model building are lambda and epsilon, so the number of instances in the model and the likelihood that they were from the full set in contrast to the canonical set, respectively. In the table here, we can see which instances are canonical and which are not, as implemented within mReasoner. Focusing on canonicality, we had two approaches. We first derived epsilon values based on the participants' provided models, such that it reflects the ratio of non-canonical entities. And afterwards, we fed mReasoner to the task responses and analyzed its created models. For this part, we first had a fixed lambda of 10 in order to reflect the experimental setup, and we ensured that epsilon reflects the proportion of non-canonical instances to have a direct comparison between the model and responses. Afterwards, we also tested mReasoner with a free lambda parameter fitting, obtaining results with the intended configuration. This figure illustrates the distribution of specific epsilon values in different comparison scenarios. So here in the top left, we can see the distribution of epsilon values derived directly from the participants' models by calculating the ratio of non-canonical instances. And right next to it, we see the epsilon distribution when fitting mReasoner to the task responses and having a fixed value of 10 for number of instances. So we can see that they are substantially different, but no significant correlation between the distributions was found. In the bottom two figures, we do not have a fixed number of instances. In the bottom left, the best fitting epsilon values are depicted, and in the right one, the so-called estimated epsilon values based on the actual proportion of non-canonical instances. Once again, we found no correlation between either one of these values and the originally derived epsilon values. What is important to note is that out of 10 possible values for epsilon in the grid search, there were on average 6.1 and 6.6 values, leading to the same response in the fixed lambda and in the regular approach, respectively. So, in our work, we investigated two research questions regarding mental model building processes in syllogistic reasoning. For research question 1, we looked into what kind of mental models individuals create when presented with syllogistic premises. We designed and conducted an experiment centered around an imaginary world of colorful shapes with marks where participants provided a visual representation and selected a response. We found the belief bias tendency, or in other words, individuals might be hesitant to conclude NVC when having some background knowledge about the existence of other shapes, for example, which can be interesting for potential belief bias investigations in a controlled environment. Regarding the mental models, 82% of them were correct representations, meaning that individuals were generally able to understand and interpret syllogisms. We found preferred mental models for 46 out of 64 syllogisms, some occurring more often than others. For the second research question, we looked into the canonicality of models, whether it influences response correctness, and ultimately whether the observed behavior is in line with mReasoner's model building process. We first contrasted correlation analysis between response correctness and derived epsilon values based on observed non-canonicality proportions, and between the response correctness and the fitted M-Reasoner epsilon values, first with fixed 10 values and then with the regular intended configuration. No significant correlation was found in any scenario, which points to the models being potentially irrelevant for the responses. However, it is also possible that the built models are not necessarily used for the reasoning portion of the experiment. In MMT, the model building part is rather important. However, we found that the canonicality parameter in MReasoner can have more than 6 out of 10 values on average that lead to the same answer, which raises the question whether two model building parameters are really necessary from a complexity perspective. On the other hand, one of MReasoner's assumptions is that humans build correct representations, and that is mostly in line with our observations. So let's focus on NVC for a moment, though. One single model is not sufficient for deducing a contradiction. We either use some additional processes like searching for counterexamples or some sort of a heuristic, or we create and test multiple different models. By definition, though, MReasoner does not build two models for MVC, but it assumes a correct initial representation that is then manipulated later to add counterexamples. To summarize, we can conclude that individuals do have preferred mental models for a large portion of the syllogisms. However, the initially built models are not substantial for finding conclusions, but the instances of a final representation seem to be appropriately chosen in line with the premises. That indicates that in contrast to manipulation of an existing model as proposed and implemented by MReasoner, the model building phase seems to be an easy task for humans. So therefore, a rather plausible way to solve tasks would in fact be a repeated construction of models. And with this, I finish my talk, and I would like to thank you all for your attention.